Yeah, you look up.
All right. So I have a lot to cover. So just any question that is unrelated to the discussion, less related or very tangential, we can move it to the back. So that I would like to cover most of, but if anything is not clear or if you need help in understanding, then please ask immediately. But other questions, you can move to the end. So what is, why do formal verification? So there was a paper in PLDI 2011, and they did a randomized framework to find out bugs in C compilers, and they found hundreds of previously unknown bugs in all C compilers they tested. The only compiler that did not have any bug was this ComCert C compiler, which was proven correct in Coq. Actually, they did find some bugs in this compiler also, but that was in the part that was not proven correct. So there was some shallow front end that was not proven correct, and there was a bug in that part, but there was no bug absolutely in their test. And they found hundreds of unknown bugs in other compilers. So in my opinion, like this is the highest level of insurance. If you want the highest level of insurance, that's the way to go. Historically, it was very difficult to do, but these days with better automation and LLMs, it seems it can be, we'll get into those details. It seems more and more tractable. Okay, so to do formal verification, the first thing we have to do is to write a spec. So we'll see a demo. So let's take the simplest function, the simplest spec possibly. So this is the function foo that I'm writing the spec of. And here is the spec. So one of the precondition is that there is a global variable x, and that must store some primitive value x. So xv is some Coq number z. So this is quantified over xv. So it's saying that at global x, there is a primitive unsigned integer, and the value that is stored at that location, I'm calling it xv. So I'm relating that to a mathematical number in Coq. And this half says that we have half ownership of that memory location. I'll get to ownership more, but roughly if you are reading some location, you just need any fraction permission works. If you're writing, you need full one permission. And another precondition is that there is a global y where there can be anything in that y. I don't care what there is in y. It can also be uninitialized. In this case, it is actually uninitialized. So it says that any R means that it can have any value or it can be completely uninitialized. But we need the full one permission, the full one ownership of that location. Because we are writing to it, we must need full ownership one of this location. And those are the two preconditions. And the post condition says that y has the value xv plus 1. So basically, x had the value xv. So at the end, y would have xv plus 1, and x will remain as before. So does this spec make sense? So there is a bug in this spec. Can somebody tell me what is a bug in this spec?
The code has a concrete value 0 instead of any value xv.
Sorry, can you repeat, Bruce?
Sorry, the code has the C++ code has a concrete value 0 initializing x, whereas the spec has any value xv. So I guess the spec sort of subsumes the particular code instance, but they are different.
But that's like before the function, the y is actually uninitialized, right? So that's a pre. So that is describing the state before the function. So before the function, pre is uninitialized. Sorry, y is uninitialized. So
I'm talking about x. X is initialized to 0, whereas the spec says that it's any value. I guess it's not a bug in the spec, but it's different to what's written down.
Right. Yeah. So that's not a bug. You're right. It's like the spec is stronger than necessary. but that's a good thing. So that's not a bug. That's a good point, though. Okay, so let's look at the proof and we'll see the bug. I guess somebody please unmute so that we're hearing echoes. So let's look at the proof and we'll see what the bug is. The proof will tell me what the bug is. So after we write the spec, we can play this very addictive game of a cock proof. And so we will see how it works. And this is like, I'll show this proof in this is a very small function. So I'll just show this proof in very gory details. And I want you to understand what is actually going on in the proof. So I want you to like focus, and please stop me if anything is not clear, please stop me immediately. It's important to understand what actually goes on in the proof. So let's start. So we're saying we are verifying the spec. Okay. So so this is the proof. So we started the proof, and on the right hand side you have this goal window where code tells me what we have to prove, and in the left we have some commands that tell how to make progress in the proof. And you should ignore, there are these numbers on the left side. You should just ignore them. There are offsets to highlight. I should have hidden them somehow, but please try to ignore them and focus on the highlights. So on the left, that's highlighted. On the right, what is highlighted is like we start from the initial state. It's saying that we start from that state, and then when we run the code, so when we run the body of the function, we should get that post condition. So that's what the initial goal is. And then we start playing this game where we symbolically execute this code one by one. So already you can see like this even though the function itself is small, on the right, what is highlighted is like the abstract syntax tree. Like this, there is a Clang plugin that gets the abstract syntax tree and it converts that to a calc, like 1:1 conversion. So you can see these things like there is this global X and it's converted from a L value to an R value and cast, and then you do addition and we assign it to Y and so on. So that's the abstract syntax. So now the game is we step this code one at a time symbolically. We symbolically execute this program. So we do the first step here. So that's the first step. So the first step is writing to Y. So we are executing that part. Is highlighted on the bottom. So we're writing to Y. We're writing 0 to Y. And so it's like a transaction. You can think of every code step as a transaction, and every transaction has some precondition and has some postcondition. So the precondition of writing to Y is that Y, you should have full ownership of Y, and it can be anything. And fortunately, that's exactly what we have in our context. So this is so that's exactly what we have in our assumption. So we can satisfy this requirement from.
Yeah, so I think I know maybe what's wrong with the spec.
Yeah.
The precondition is just like the X value is anything, right?
Yeah, that's fine. Yeah, that's fine.
That's fine.
Yeah, because you see, like what Quark is asking, what the semantics is asking me is exactly what I have. So this part is fine. So these two cancel out. So when I do the next step, these two would cancel out. So what you note is that our wallet, you can think of our wallet. So we have our wallet, and in our wallet, we lost the ownership of Y because we are writing to Y, and that command has full ownership of Y as a precondition. So we lost. It's like this transaction of writing to Y requires 1 Bitcoin, and that's to do that transaction, you have to give up that token from your wallet. So it's gone. But fortunately, when the write finishes, we get back the ownership of Y, and now it has the value 0. Does this make sense? It's like you can think of it like Uniswap, like you swap your precondition for the post condition, and you keep doing it. You have a wallet, you have things inside your wallet, and at every step you have to give up the precondition of that command, and you get back the post condition of that command. And we keep playing this game. So that was the first step of the game, that was writing to Y. And any questions so far?
Yes, so on top there is the goals, and then there is what I currently have, and then it's how it's interpreted. Is this how it works? Like the dashed lines.
Yeah,
Can you explain the different parts of what we actually see?
Yeah,
It's
like
it's completely good.
goal, what I have, how I'm proceeding. Is that how
yeah.
it
So
works?
this part is what is the state of the world and the tokens that we own right now. So when we start a proof, we own the preconditions. So this is what we own right now, and there are also these things. This is also what we own, but those are like things that are persistent, like things that never change. The type of the intrinsic type of a variable never changes. So it's these things can be. I'll get into those details later a little bit.
Can I ask, is the problem with the spec that we are dealing with like canonical integers which don't overflow in coq versus like
Yeah, that's right. Yeah, that's right. We'll get to it
Yeah.
soon. Yeah, good call. Okay, so now we go to the next step, which is reading X, right? So we are reading X. Oh yeah, sorry, why I went from yeah. So the next step is yeah. So we are evaluating this operand plus. So we are first trying to evaluate the left hand side of plus. So plus is an operator. We have to evaluate the both sides. So we are evaluating the operand x. So evaluating that operand x requires reading x. So that's the next step. Now Coq is asking me the precondition for reading x. And if you look at it, the precondition says that you should show that x has some value v. It can be anything. It cannot be uninitialized. If you're reading something, it cannot be uninitialized. It must be initialized, and it should have some value v. So we have to show that, and we fortunately have that. We know that the precondition says that the x has some value xv. That's fine. So we'll instantiate v by xv, and you see that the read would return the value v. So you see that the same v is used as the left hand side to the addition. So the read would return the value v, and it also shows that you can have any fraction q. So that's what I was saying. For read, any fraction q works. And fractions are between 0 and 1. And qp means positive fraction. So it has to be positive. So any positive fraction works. That's why half works. So we'll instantiate q by half. So that's what we're doing in the next step. We're instantiating q by half and v by xv. So this is like, we don't really need to do this manually. I'm just showing you just one last proof in a very manual way, just to explain what's going on. So read is like a free transaction. The precondition is the same as post condition. So our wallet remains the same. So the next step, the next step is addition. So now we have evaluated both sides of the plus operator. So now we can add them. Add unsigned addition is also free. Like there is no precondition. We'll see that signed addition has a precondition, but unsigned addition has no precondition, so it's free. So there's nothing to do there. And now the final part is we are actually writing to y. So and that has same as before. It has the precondition that you should show that y has anything, but full ownership. Because now there is a slight problem here that what we have is not any. What we have is that y has some value 0. And what we are required to show is any. So this doesn't cancel out as it is. But there is a lemma saying that if you have a primar, that implies any. So we can rewrite with that lemma. And now we have converted the primar to any. And now things cancel out. So now again, we have lost y from the wallet. That's fine. When the write finishes, we get back y, full ownership of y, and now it has the value. Now it has that value, xv plus 1 mod 2 to the 32. And so as Sam was saying, this is the bug. So let's wait. So now what has happened is now we have finished executing the code. So the rule of the game says that once you have finished executing the code, whatever is in the wallet must match the post condition. So the post condition is that part, and we have this in the wallet. And if you see that the X part is completely matching. So but for X, whatever we have is exactly what we have in our wallet. So those match up, no problem. But for Y, what we have doesn't match. The post condition required XV plus 1, and what the semantics computed was XV plus 1 mod to do the 32. So we lose in this game. So just to summarize, I think it's important to understand the rules of the game. We start from the precondition, and we symbolically execute every AST node. The semantics defines the precondition and postcondition of every node. And at every step, we have to give up the precondition. And when that command finishes, we get back the postcondition, and then we continue. At the end, we have to show that whatever we are left with matches the postcondition. So there are two ways we can lose. As before, at the end, we saw that there was a postcondition mismatch. We can also lose even before executing the program, where some operation we don't have the precondition. So let's see that example. So I've changed the spec of foo, and I've dropped the ownership of y. So in this case, if when we start executing, we lose even before we have finished. We still have code to execute, and we have already lost. It requires the cork is asking me for ownership of y, and we don't have that. So we lose. Enough losing. So we fixed the spec now. So now we just add this mod, and now this proof just goes through. Okay, so that was the first example. The next example is similar. Just I changed the signed to with unsigned it. Now somebody tell me what is the bug in this spec?
So it's the same code, or?
Sorry, I'm sorry. Yeah, that's a really, the code is this one.
Well, in this case, your spec does disagree with the code. You've got the concrete value 1 in both integers in the spec and 0 in the code.
No, sorry.
I think that's the ownership.
Sorry, yeah,
That's
that is
ownership.
indeed the ownership. Sorry, I'm still parsing this in my head.
Yeah, sorry. Yeah.
The post conditions still just X plus 1 mod Z.
That's right. Actually, the bug is in the precondition. There is a missing precondition. So we can look at the proof and see. So we can ask Cork for the proof, and Cork will tell me what is wrong. So
Can we wait like another?
The natural numbers and the
Yeah, just trying to see what's the precondition.
it's the natural numbers versus signed integer for y. I mean b.
oh yeah, that was a mistake on my part. But yeah, there is still a bug.
Question, we're just reading A, so why do we put full ownership? Maybe I'm misunderstood.
Yeah, it's just I'm simplifying it. Yeah, so you're right. This is not an ideal spec, not the optimal spec, not the most expressive spec. I mean, not the strongest spec. But yeah, so that's also, you can say that's a bug. But there is something else. Like this is not even provable. Like the spec. So this one, that issue doesn't prevent actually proving it. I will be proving a weaker spec, but I'm saying that this spec is not even provable. There is a bug that makes this spec unprovable.
Could you go back to the previous spec too real fast?
Yeah. I can try to open both. Yeah, so now we have both. This
Is
is the
it-
spec.
Is it again just a case of you don't like your precondition is too weak and so you don't have the right bounds and can't prove that if you what was it add them together or add one that you don't again overflow or underflow or something
it's
like
the
that?
same thing. Yeah. So it's not like a super interesting bug. So let's not spend too much time. So if we on this, so if we prove it, Coq asked me to prove that this is, I should have, so this is essentially asking, Coq is asking me to prove that xv plus 1 is within the range of integers. So for unsigned integers, the rule is that there should be no overflow. Any overflow is undefined behavior for unsigned integers. So we have to add that in the precondition. So once we add that in the precondition, we choose xv so that it doesn't overflow. Like then Coq can prove it.
But do you have to do that in the precondition, or could you also incorporate that as you could make the postconditional implication where you say, assuming that it's, in this case.
No. So we have to. So we lose even before we finish the game, right? The game requires. So yeah, exactly. So if we see this, we don't even reach the postcondition. Like we lose even before, just at the time we do addition, we lose. The precondition for addition is not met. So we don't. So we will leave it to fix that. So if we really want no precondition, we have to do we have to change the code to do something else in the case there will be an overflow.
So signed addition requires not overflow.
So some of my colleagues who defined the semantics, they went into the C standard and they did pretty good work. So I have not looked at it, but I believe them that they did a correct encoding of the standard in Coq.
So sorry, so quick question. So here, is it a case that, before you do proof in Coq, you need to understand what's the semantic in Coq about an integer versus an unsigned integer? Like if it's like there's mismatch between maybe what we think are the preconditions, like for example, for unsigned integer, it seems it was automatically, looking at, modulo 2 power 32, whereas it's not doing that for integers. So is it the case of like we need to know what Coq assumes to know about different types?
It's not a Coq problem. It's a problem of the semantics. That's how the C++ standard defines the semantics. We don't want our code, even if you don't do this proof in Coq, even if you don't do any proof in Coq, if you're writing C++ code, you need to know what the standard defines as undefined behavior. So like if your program has undefined behavior, the compiler is free to like nuke the word. So that's the contract with compiler writers. Like compilers can do whatever they want if your code has undefined behavior. So when we write C++ code, we have to make sure there is no undefined behavior. So this has nothing to do with if C++ has nicer semantics, the Coq thing would be nicer, but sadly the C++ standard is what it is. So
I still don't understand how it works like that. We can't even get to the postcondition. So let's assume that my postcondition is true. Then it should always verify it true, right? I mean, if my function has a postcondition true, then no matter what the precondition is, it's correct.
You still need to like have enough ownership to execute all the code. Your precondition should...
okay, so it's about the ownership of the
ownership, and also like the code should not do an undefined reference. Like the code cannot, even if you have postcondition true, you cannot prove anything about the code that like references undefined variables, like a deleted variable, undefined array accesses. So those are still prevented. Like even if your postcondition is true, if you have verified the code, it means that it doesn't have undefined behavior.
And not having an overflow is something that I need to kind of have.
Whatever the C++ standard defines as undefined behavior, that has been encoded. Okay. So there are many things like array accesses have to be in bound. You cannot access undefined memory, like unallocated memory. All those things are undefined behavior and they're ruled out, even regardless of your postcondition. Okay, so let's move on. So we are 30 minutes. Okay, so let's look a little bit under the hood. So pre and post conditions, the things that we wrote down in that notation, those elements are of type empred in Coq. And that's different from the type prop in Coq. So if you've done any Coq programming, like typical assertions that you write and anything that you prove that has type prop is called a proposition. So this proposition says that BV is a prime number. And you can prove that. When we are doing separation logic proofs, the pre-post conditions are not prop. They have type empred. And the difference is that empreds can implicitly talk about the state of the memory. So when you're saying that this global has some value X, you're implicitly talking about the state of the memory. And like people have done this, use the same separation logic to do even other things like verify distributed programs. And they've generalized this concept of memory to like state of the world. So in general, separation logic assertions, they have type empred, and they can talk in general about the state of the world. It could be memory, but people have generalized that to do things like in distributed system proofs, there are packets in the network and so on. Okay, so this was the assertion that we saw previously, like the global B has this value BV. That has type.
Sorry.
Yes.
Can I ask, is empred part of like Coq's standard library, or is it built in, or is it a part of a library that someone defined?
So empred is a part of the iris separation logic. So it's a very general separation logic. It has been used for many kinds of proof. We won the Test of Time award just this year. So they define empred. So you can use, and they define something that we used to define empred. Like we just add a little bit of like C++ specific things to what they define, and it's a thin wrapper over this iris definition of iprop. So yeah, so it's mostly defined by iris separation logic. It's which is a third party separation logic library. Okay, so empred, we can talk about the state of variables, state of memory like this. Another thing we can do is empred is like embed pure propositions. So if you have any pure proposition, like which doesn't talk about memory, we can embed that in this empred using this notation. So for example, BV equals 0, we can write it like this. So this is useful, for example, if you have a function which guarantees that at the end of the function, B must have a prime number, then we can say that there exists some BV such that at B we have BV and BV is prime. So this can be used as a post condition of a function that guarantees that it stores a prime number to the location B. Right. So and how do we put empreds together? So for props, we usually put them together by AND, saying P and Q. But for empreds, the typical way to put them together is this double star. And this double star is slightly different. It's like a conjunction, but it's slightly different because it also talks about ownership. So the key to show, one way to illustrate this difference is that if you have a prop, you can freely duplicate it. So P implies P and P. So it's like knowledge. Knowledge you can freely share. You can just tell anybody. You don't need money to. Anyway, so but in case of empreds, we cannot freely duplicate empreds. So this is saying that if you have full ownership of the location X, you cannot take this ownership and duplicate it into two pieces. So that's disallowed. So that's the main difference in empred. But it still holds when you embed a pure thing inside empred, you can duplicate that. So that part is true. Like it was still knowledge. We embedded some knowledge into empred. You are free to duplicate it.
Sorry, another question, but there presumably is some limited form of copying, right? Like if you have full ownership of X, then presumably.
We'll get to that.
Oh, sorry.
That's fine. Yeah. So this is an example empred. Now I want to go a little deep into this notation, this points to notation. In separation logic literature, it's called points to. So on the left of it, there is a memory location. So the memory locations have this type pointer in the logic. And so like global B is a memory location. So the left-hand side of the points to arrow must be a memory location. The right-hand side should have type rep. So it says like it's a memory representation. So what is a memory representation? It defines how some high-level mathematical Coq object can be laid out in memory. So this is saying that how to like how this mathematical number in Coq is represented in memory. So this prim_r is something that is built into the logic, like that is defined by the logic, axiomatized by the logic, but we can also define our own rep predicate. So we'll see in this tutorial, hopefully, that let's say we have this struct which stores unbounded integers, right? So we have an array of uint. So we can store, instead of like 32-bit, we can store unbounded integers, and we can define our own memory representation for that type. So ultimately, memory representation, the job of memory representation is to show how this some logical abstraction of that object, how that is laid out in memory, and what is the ownership, how much ownership we have for that. So that's what goes to the right hand side of the arrow. So and so this prim_r was for primitives, and there are many primitives. So another primitive is a pointer. So for that, let's look at this thing. So this is a integer pointer, right? So in prim_r, we can also say like prim_r, the last argument, instead of being a number, it can also be a v pointer of some memory location. So this is saying that the location has the representation of a memory location. So we'll use this in the spec of this function. So this very simple function to illustrate that. So it stores the address of A into pointer. And so here is the spec. So the spec says that the precondition is that the pointer has anything. This location, this global location pointer has anything. And the post condition is that at the end, it has the location of the global A. Makes sense? And again, the Coq can prove it automatically. So, and we have been seeing this notation for a while. This means implication. So this is like logical implication. But it's a little bit more than logical implication because it also says that the ownership of in L is a superset of the ownership in R. And then we can connect these two empirics by this to make a proposition, and then we can prove statements like this. So anything we prove in Coq it must be a proposition. So this defines an embedded separation logic in Coq. So to give an example, this is not provable, even though both the left-hand side and right-hand side of the implication are the same. Like they say that the x has the value 0. The fraction on the left is less than the fraction on the right. So this is not provable.
Is it a problem if we lose permissions, like if we lose ownership? I mean, we could write it in the opposite way around, right?
Yeah,
and it would be correct. But it might be a problem because we end up with something that's too weak, I guess.
Yeah, in this logic, there are variants of separation logic where that's not allowed, but in this one, it's allowed.
Okay.
It's still our automation wants, like it would not automatically prove. If I switch the order, the automation would not prove it. It warns us that you're losing resource. Sometimes it's a helpful thing in proofs. Like if your code is losing ownership, there is probably a memory leak. And so it's an early warning. Like usually if you finish the proof, you'll find it anyway, but it helps in finding it earlier. But this logic iris is set up in a way where it's fine to lose ownership.
Can I ask, what's
Yes.
the reason for the fractions?
Yes, we'll get to it next.
Sorry.
Yeah, next. Just one more thing before we get to it. So we wrote the preconditions in separate lines, but that's like just a shorthand for writing this. Like we just, all the preconditions, everything in pre is just start together. So they're essentially saying the same thing. Okay, so, okay, we have a little more before we get to fraction splitting. We haven't seen any spec that, so far we haven't seen any spec that actually had arguments. So this, I'm trying to show what happens when we write specs of a function that has arguments. So this is an example, it's a very simple function GCD. So there is no ownership being passed or received, like everything is passed by copying. So no ownership is passed. And so there is this arg notation, arg keyword, which says that there is an argument named AV. So this saying that in C++ it has name A. And that argument must have some primitive integer AV. And AV, so we are saying that let AV be the value that it is in Cork. So it must not be uninitialized, and it must have, anyway, these arguments are cannot be uninitialized anyway. So we are saying that AV, in this spec, let AV be the value that is being passed in. And for B, let BV be the value that is being passed in. And in post condition, we have this square brackets to define, to say like, what is the return value? So this is saying that the value that is being returned must be the GCD of A and B. And yes. And this amp is like, what is the ownership? Like if you're returning something and if you're also returning some ownership to the caller, then we put it here. Here, there is no ownership being passed. Even nothing is being, no ownership is being passed in, no ownership is being passed out. So this is amp. We'll see another example where that's not the case. So so somebody mute yourself, please. Or if you have a question, if somebody wants to ask a question, please ask. Okay, so we don't normally pass arguments by value in monad because we often pass bulky things and we pass them by reference. So let's look at an example of the spec of this function where we pass by reference. So we pass the arguments by reference. So here, what we're getting at A now is not an integer. What we're getting at A is a memory location. When we pass things by reference or we pass things by pointers, what we get at the argument is not an integer value. What we get is a memory location. So the argument just has a memory location. And then we separately have a precondition saying that at AP, at that location, there must be a primitive integer AB. And we should have some fraction ownership QA for that. Because we're only reading A and B, so fraction suffices. And there's this new keyword pre-post saying that this is also a post condition. This is just a shorthand to make specs more readable. This is saying that this is also a post condition so that we don't need to write that separately here. Seems the same for B. And even the result argument is a memory location. And we have a precondition saying that you have to give up full ownership of, the caller must give up full ownership of that result location. So the caller cannot concurrently write to that during the call or even read it because they have given the full ownership, and reading requires at least a little bit of fraction. So the caller cannot even read this while the GCD call is in progress. And the post condition is that at that memory location, the value would be GCD AB at the end of the call. Does that make sense?
Can you show us the proof?
I have the proof, but I can show at the end of the lecture. This is not in the main thread. I want to get to Sam's question. But the proof is in this file and I can show you at the end. So now let's get to Sam's question. Why fractions? What do we do with fractions? So we saw that reading required only less fraction and writing required full fraction. But what that helps with is concurrency. So in Haskell, there is this, sorry, not in Haskell, in Rust, there is this slogan called unrestricted mixing of aliasing and mutability is bad. The same idea, like if you have, so this is an example. So if you have a fraction ownership of this location P, then you can split it into two pieces. One piece has q by 2 fraction and the other piece has q by 2 fraction. You can split it anyway, q by 3, q by 2, q by 3. You can, anyway, that adds up to q. You can split the fractions. That's the key thing. And now what you can do is you can give one piece to one thread and give another piece to another thread.
What does the dash r dash mean?
That's equivalence. Like in MPEG, that's equivalent. So that's the key part. That enables read concurrency. Like if two threads are reading, you can split up the fraction and give a piece to both threads so that both can read. Because reading requires any fraction. So q by 2 works as good as q for reading. So we'll see an example right now.
Why might I have any other fraction than 1 over n, where n is the number of threads? Like, why doesn't that suffice always?
Yeah, that usually at the end, so many of the specs keep q, they quantify over q, like here I've quantified over q. And at the end of the day, like when we're writing the top level main function, then we decide who gets what fraction, how many threads are there, how many people are accessing. At that time, we do the accounting. But in these library specs, we just keep quantifying over q. Yes.
But in this particular GCD function, we actually write to A and B, right? So we would need full.
No, we don't write in the GCD function. We just read. No. So in this function, this A and B are passed by a copy, right? We make a copy. Okay. So, but we will see a place where we need it. So that's the next example. So so how this thread splitting works, that's the next example. But so just to first before Coq, we get into Coq, let's look at how multi-threading works. I think this is also a very key part. So please pay attention. This is also like separation logic is great for concurrency. Like it really shines in doing concurrency proof. So this is one of the key things. So how do we do create a new thread? So let's say we are the parent thread is running, like the main function is running, and it has the ownership P, right? And now it wants to create a new child thread. So before that, what it has to do is to split this P into two parts, PK and C. So C will be the ownership it will give to the child, and PK is the ownership that it will keep for itself. So now we have split this into two threads. Now two threads are running. The parent is running with PK and the child is running with C. And the parent would do some operations that will mutate its ownership, and the ownership at the end will be PK prime, and the C ownership will become C prime. And then at some point, the parent may call child.join. And the child has finished. And at that time, parent gets back the C prime. So at that time, parent continues with PK prime and C. So we will see all this in Coq, but this is the picture I want you to keep in mind. Okay, so we'll see the spec of this function now to see that parallelism. So this function, it may be a little contrived, but if you just pretend that these A and B's are like 1000-bit numbers, then it won't feel very contrived. So now we have to compute both the GCD and the LCM. So what we do is we start a thread that computes GCD. So we create a thread and we start that thread. And while that thread is running, we compute the product. Again, this can be 1000-bit numbers, so this product can be expensive. So we are doing two expensive operations in parallel. And then we join, and then we compute the LCM. So we are doing at least two operations in parallel. Make sense? So we'll go through the proof of this function next. So let's look at the spec. So before we write the proof, we have to see the spec. So the GCD part is the same. Like as before, we have AP, BP as passed as by reference, and we have this result pointer, preconditions NER, and postcondition says that you should have the GCD value. The only new thing is this LCM. So for LCM, we have another argument. The precondition is the standard, but the postcondition is interesting. The postcondition says that if there was no overflow, then it has LCM. But if otherwise, it has some garbage, no guarantees. Make sense? Okay, so we are using a thread library here. So, and whenever we do a proof of function that calls any other functions, we need specs of those functions. So we need specs of the threading library. So I'll show you the specs quickly. So this is the thread constructor. So this is the picture, the ASCII art that I showed just before. This makes that formal in Cork, like how we split and all that. These specs make that very precise in Cork. So what this threading library does, it takes a lambda. And so that's why there is this argument saying that it must be a memory location because it's passed by reference. And at that location, we have ownership. We should have ownership of the lambda struct. If you are a C++ nerd, you know that lambdas are represented as structs, like all the captures, they become fields of the struct. Anyway, so you need ownership of that struct. You need to pass in the ownership of that struct, and you get that back. This thread library copies that lambda. And this is the key part. So you have to come up with, the caller has to come up with a precondition and a postcondition of the lambda function. And the caller has to prove that the lambda function has that precondition and postcondition. The only extra postcondition is that the lambda function can also read the fields of the struct. So that's given, but other than that, the caller has to pick a lambda function and pick some precondition and postcondition of the lambda function. And once the caller has done that, then the caller gets this token that at this object of that thread, like at the object base pointer, there is a memory representation of a thread that has this lambda and this precondition and that postcondition. And so the main thing is like, how do we use this thread R? So we'll see how do we, the use of this becomes clear very soon when we look at the next functions. So one of the next functions is start. So what is the spec of the start function? So it says that you need to give that thread R. And that we get when we construct a thread, we get that as a postcondition. So we can pass that into start. So we need to give that as a precondition. If we don't get that back, instead what we get back is this token saying thread has been started, thread started. And this is the most important thing. Like whatever was the precondition of the lambda function, you have to give up at this point. And you do not get it back. So this is not a prepost, saying that when you start a thread, you have to give up whatever was the precondition of that lambda function, and you do not get it back.
What is the pre-post? So there's post, and here it says pre-post as well.
You're talking about this one?
Yeah, exactly.
So this is just reading saying that this is both a precondition and a postcondition. It's just reducing some duplication.
Okay, yeah.
Okay, so the spec of start, does the spec of start make sense? Like it just formalizes this diagram, like in that diagram where we lost the ownership of C, the parent thread has to continue with PK and lost the ownership of C, is just making that formal here, saying that you have to prove that the thread has the lambda has some precondition, and when you actually start that thread, then you have to give up the precondition, because after that the function may start running. So you better give it give that precondition to that thread, and you lose that. But when you call join, so the next is join. So one of the precondition is that thread started. So you can only call join on a thread that has started. So even though you don't understand, you don't need to really understand the meaning of thread started or how it's defined. Just by reading the spec, you can understand the protocol. This is enforcing the protocol, saying that only on a started thread you can call join. So once the thread is started, you can call join. And one interesting post condition is that when you call join, you get back the post condition of the lambda. So the Lambda has finished executing. So whatever was the post condition at this point, when you call join, you get that back. So this is like in the diagram, we were getting that C prime. So this is like the C prime in that diagram. So we get back, and now we get a token that the thread is done. And once the thread is done, basically you cannot do anything with it. The only thing you can do is call the destructor. So there are a few things like just this this is not very long, and you can just read off the protocol from this, like these constraints, like only on a started thread you can call join, and so on, and is clarified, and also concurrency is clarified. There is no fraction, so this means there is no fraction, so which implies that you cannot split a thread, which implies that you cannot really pass a thread, and you cannot concurrently call these start methods, on threads from different threads on the same thread object. So even the concurrency is clarified because there are no fractions in these predicates. Okay, so we'll use these specs to prove the parallel function that we just saw. Okay, so just a minor thing, what happens at function calls? If we So yeah, back to that function. So what happens that in function calls? So when we do a proof, we must have like in our wallet all the specs of all the functions we could be calling. So if we start this proof, the proof of this function, this just stops. It stops because there's this constructor that being called. The constructor of the thread is being called, and we do not have any spec for it, and so we lose. So what we must have is in our wallet all the specifications of all the functions that we are calling. And some of the specifications can be just like inline the body. So like here I'm saying that the specification of the destructor of the Lambda is just to inline it, and that becomes the specification. So that's an option, easy option. Like if we have some tiny wrapper, you don't really need to write a specification. You can just tell the automation to inline it. And this GCD spec is proven later on in this file. So that's why I'm assuming it here. But this assumption can be removed later because it's proven. Okay, so we start the proof. So the first thing that is happening is, so now it's like unfolding the huge abstract syntax tree, and the first thing that happened is this call to the constructor. This is the first thing this function does, is constructs this thread object. So there is a call to this constructor. So functions you can think of as like jumbo commands. So it's the same, the rules of the game are the same. Like even for function calls, what you have to do is you need to give up the precondition of the function you're calling. So this is a thread being calling, so you need to give up all the preconditions. So everything that was quantified here, we have to choose the values and give up these tokens. So it's saying that there was this Lambda struct ownership that was quantified. We need to now pick the value. There was this task pre and task post, and the caller has to choose the values. So what is the pre and post condition of the Lambda function? That is of this Lambda function. We have to pick those things here. So the first thing is Lambda, the ownership of the Lambda. That part is actually automatic, so we don't need to manually. So there's an automatic way to pick the Lambda. So the main thing is to construct this task precondition. So we are executing a Lambda. So what is the ownership that we need to give to this thread? That is task pre. And now we have to choose this. So this task pre is computing GCD on AB and result. So we give it ownership of AP. We just give it half ownership of A and half ownership of B and full ownership of the GCD. location, right? Because it's storing the result. So we give it full ownership of the GCD. And that works because the rest of the code is actually not touching GCD result. It's not even reading it until we call join. So that's fine. And by join, we'll get back this ownership. So this is fine because we are not actually even reading GCD result until we call join. And we give half ownership of A and B locations to that thread. And also that works because we still have the half. So one thing is like, we don't really need to instantiate the task post condition. It can be done completely automatically. So
why is half coded here? Does it have to be half?
no, it can be 1 by 3, 1 by 3, 2 by 3, whatever. You just split two pieces.
So we could do it how it was before with there exists a fraction that you can do it, right? Like
I mean, but we have to split. We are given a fraction. We have to split it somehow, and half it just works as good. So it's just a simple thing to do. So
You have to give a concrete fraction, right?
yeah, at this point we have to give a concrete fraction.
And does it have to sum up to 1?
It does. I mean, q by it has to sum up to q. We started with the q. So yeah. So now. Okay, so the next spec is the next part is we have to prove this the last precondition. One of the main precondition of the thread constructor was this part, that we have to prove that the lambda, once we have already chosen task pre. Now we have to prove that the lambda has this specification. So we have to prove that specification for the concrete lambda we are passing. Right, so now Coq is asking me to prove this part of the precondition. Now basically Coq is asking me to prove that precondition for the specific choices that I've already made. Okay, so now we get inside this, we're proving this precondition. So we are proving a specification. So as if we are proving a function, we say like verify the specification. And this proof is completely automatic because we already have a spec of GCD. So, and this is just a simple call to GCD. This proof is completely automatic. And so we ran through the body of the GCD or body of the lambda. And this was what we ended up with. And this is what I was saying, that the post condition can be inferred automatically. So any post condition of that lambda has to be implied by this. So the strongest post condition is just bundle these together. Right, so that's the algorithm. We don't really need to come up with a post condition that can be automatically computed. You run through the lambda and whatever, using the precondition that you chose, and whatever you're left up with at the end of the lambda, that is the most strongest post condition anyway. So we just instantiate it automatically. Okay, so now we are done with the thread constructor, and what we are left with now, the next step is the call to the start. So t1.start. Right, so now in the code, we are invoking start. So we are there, we are verifying that part. So here is so if you look at the spec of start, So here the main thing is, so when this is the main thing that we have to give up the precondition when we are starting the thread. So whatever we chose at the precondition, at this point, we have to give that up. And before that, so here is the precondition. So when we are doing the proof of start, so this just gave me the precondition. So like if you see like thread R is a precondition, and that's what Coq is asking me to prove, thread R. For the concrete choices that I've already made. And then this pre is what Coq is asking me to prove here. This is the pre we chose before. So Coq is asking me to prove the preconditions of the start. And again, so this exactly matches with that. So no problem. Coq just cancels it out and so what we are left with at this point is like half ownership. This part, like the thread demands half ownership of AV and BV. So that's what we have to give. And what we have is QA, and what is needed is QA by 2. So there are lemmas to like split the ownership. So what happened now is you can see that this AP that got split into two pieces. The ownership of AP got split into two pieces, same with BP. So this is the split. This is where fractional ownership helps. We split that using the lemma. And now see, now we're done with start. And we're only left with Q by 2 of A and B. But that suffices to do this product. And we have lost the ownership of GCD result pointer. The other thread has it now. So the next step is now call to join. So we have done the product. Now we do the product. I won't go through it. The next next step is the call to join. Right. So again, Cork will ask me to prove the precondition of join, which is that thread has already started, but we already have in our wallet that the thread is started because we just call thread start. So we have this thread started already in our wallet. So we can use that to justify the only precondition for join. And that goes through. Then the nice thing is that after join, we get back the ownership of GCD result. And we now know that it has the GCD value. And we also get that the thread is done. We get back the Q by 2 ownership. So now we have Q by 2, both pieces. Now we get everything back and the GCD result. So now that the GCD result is valid, it has the correct value. Now we can do the next step, which is the division. So now we are doing that division.
I have a question. What is the ownership? So I understand that the result should have ownership 1, but it says 1% modulo Q.
That's just some notation.
Okay, so ownership is 1.
Yeah, just ignore the QP. Yeah. So now we do the division. Now the division, the only thing in division is like, again, there is a division has an issue, like division has a precondition. Yeah, so the denominator should not be 0. So Cork is asking me to prove that the denominator should not be 0. And that's why I had put this in the specification. I had put this condition that either of them must be non-zero. And that is enough to prove that the GCD is non-zero. Anyway, so there are some using the standard library in Cork. Standard library has enough lemmas. So if I just
can you compute that? Like, how does it prove that the GCD is not 0, given that the arguments are not 0?
Yeah. So
is that an induction proof, or does it happen automatically, or?
No, it's just the Cork standard library has these two lemmas saying that if the GCD is 0, then either of them must be 0. Okay. So I just pull that in. I'm just telling Cork to look at, and then I have a system where we can use LLMs, and LLMs can actually look through all the lemmas in the standard library and find the relevant one. So this has been automated. Like that was the last project I did at my company, but it's just here I'm doing it manually. So with that, this precondition gets discharged, and now the final stage is like, this is what the C++ computed using the semantics. There is this ugly, again, a mod 32 here before doing the division. And also this division in C++ is code. Anyway, so there are other lemmas to, so post condition had a decide, like they had a case analysis. So now I'm asking to make the two cases. And the first case is when overflow happens. So the first case is when this is not true. So overflow happened. In that case, we have to return garbage, which is fine. Like if we have something, then we can just instantiate garbage with that. So there is no, so this case is very simple. Cork just discharges it. And the other case where we have to give the actual result, we have to actually prove that it's the LCM and not like the product of this and mod and all those. So we have to do some simplifications that Cork can do using the standard library. We can prove that both the sides are equivalent, and that finishes the proof.
Wait, so why is it okay to return garbage? Should we exclude that in the precondition, the overflow, or?
That's the post condition of the function, that if there is an overflow, then you can return garbage.
We define a post condition that if there is an overflow, we can return garbage.
Yeah, so there are many ways. So that's a good point, I think.
But earlier I asked the question and you said, oh, it's not possible to do this in the post condition. You have to
But,
do this. In
but there is no undefined behaviors. Undefined, the precondition has to rule out undefined behavior. There is no undefined behavior in returning garbage, in just returning some arbitrary number. That's like there is no.
But the overflow is
Oh, yes, we are overflow. We have put this precondition to avoid the overflow. We did, sorry, not overflow. The division by 0.
Yes.
And this, sorry, okay. I think I get your point. This is unsigned integer, so there is no precondition. Like unsigned addition, unsigned multiplication is always defined. There is no undefined behavior in unsigned multiplication. That's why.
So even if it overflows,
yeah, it's mod. So the semantics says that you will get the modular arithmetic value.
Okay, and with signed integers, here it's undefined.
Yes.
Okay, I didn't understand that. Okay, that makes sense.
Right, thanks. I have a little bit of time left. Okay, I have to skip a lot of things. GCD proof, all that. Just to go.
This in the files.
Yeah, these are in the files. Just 5 minutes left. Okay, we wanted to do arrays. We don't have time, arrays and structs. But I do want to end with the specification of execute blocks. So far we have been seeing toy examples. And let's look at something realistic. Like I've been doing a proof of this execute block function. This is the top level function at Monad. And I want you to just at least understand the spec a little bit before we go today. So this is the function that we'll see the spec of. So it takes block and executes the block. And the key thing is this variable block state. So this block state has initially it has the state before the block, and at the end this variable must have the state that corresponds to the to executing all those transactions. So that's the key part in the spec, is to specify what is the precondition and the postcondition for this memory location, for the location that is being passed in at this argument. Okay, so this is the spec. And there are a lot of arguments. You don't really need to understand everything. I just want to highlight a few things. As I was saying, that there was this block state argument that has a memory location. So the caller passes a memory location. And it says that in the beginning, it has the pre-block state. So actually what it has, it stores a diff, like it just stores a diff between what was the pre-block state and what are the changes that this block made. This is saying that at the beginning, it has the diff between pre-block state and pre-block state. So it has like it may have some storage from the pre-block state, but there is no diff. The diff is empty. So it's a diff between the identical things. That's the precondition. And the postcondition is interesting. The postcondition says that it has the postcondition, it has the difference between the pre-block state and the actual final state. And the actual final state is defined in Coq, which is just like, it just executes all the transactions one by one. So it's like a fold left on a list. We can see this function just executes all the transactions. So this is the main thing. So this is just 5 lines instead, and there is no concurrency here. Like you can see, you can just read this function and it's very clear that it's starting from S and executing the transaction T completely. And let's call the result SF. And then from that state SF, it's doing the recursive call. It's executing the rest of the transactions. Just like this is 3 lines of beautiful code, no concurrency. It's very clear that everything is being executed sequentially. You can read this and understand that there is it's simple. Obviously, like if you actually go into like the definition of this function, like what does it mean to execute a single transaction? some EVM semantics in Quark has to define that. That can be ugly. But at least this multiple transaction things, there is no concurrency issues here. In contrast, if you look at the code is very concurrent and it has a lot of complexity. So this is a very, this is one of those specs where the specification is much simpler than the implementation. Like the specification is very clean, like you execute all the transactions one by one according to some official EVM semantics. And even though the code implements it in a very complicated way, at the end of the day, the final results should match the sequential execution. Does it make sense? A little bit?
But how long does it take for this proof to run?
Execute block?
Yeah.
10 minutes,
10 minutes.
10 minutes. Yeah, there are ways to spell. So before we go, I'm sorry, time, just give me 2-3 minutes. And the next, so what's the plan next? I could not cover many things, so those will get moved to the next tutorial. But after that, I was thinking about like, today we saw like read concurrency using fractional permissions, but separation logic is like very much more powerful. Like you can split this ownership in many more complicated ways. You can say that both threads can read, both threads can write, but one thread can only change it one way. Like one thread can only increment, the other thread can only decrement. There are many different complex protocols you can set. You can split this ownership in a very rich way. And so that language is very nice. So when we're writing specs, I think that it's good to learn that language. So we'll see some examples with things like SPSEQ or locks of the other expressive ways in which we can split ownership between multiple threads in concurrency. And we'll do a little bit of deep dive into the proof of execute block. I just showed the spec, but next time we'll sketch the proof a little bit if you have time. And then after that, the plan is like we can, every session, we can pick a module in the code base and together write the spec. I think there's something like block hash buffer. I think it was very simple. I think that we can get to even the next lecture. We can together write the spec and sketch the proof. So the overall goal is like, I want like most of you to be able to write specifications. There are many advantages, like you get very precise documentation, as we saw for the thread example. Like it's very, in a very short, in few lines, it specifies the protocol and how much concurrency is allowed, and all those things are precisely specified. And once we have the spec, we can have proofs to like either prove the spec or give you a counterexample. So there's a lot of progress being made here to make those proofs more automatic. Like many of the functions here, like GCD, was automatically proven by my tool, which there's a lot of symbolic reasoning and combines that with LLMs. Like when things like loop invariants, it's hard to, there's no good algorithm, so it asks LLM for those things, and there's the rest. And if the LLM gets it wrong, it gives it feedback. Well, you made this mistake. So the main problem with LLMs is that they hallucinate, but once you tie it to Coq, they cannot hallucinate. Like if they hallucinate, you have to, Coq would tell you that you're wrong. So it's a very nice combo. And it's just that last year, like they won like the silver medal in IMO. So I think it's a very promising area that I hope to pick up. I was doing it in my last company. I hope to pick up more here. And if there's no proof, you at least get a counterexample. So that's good to write like the specs in a formal language, advantages. And also one last thing is like in my last company, often like we have here like RPC crashes, and we have like five hypotheses of why it is crashing. And in my last company, it would happen like our hypervisor crashes, and we have 5 hypotheses like why is it crashing. And we can quickly rule out many hypotheses, because that hypothesis is something that we have already proven the spec rules out. The spec, we have parts of the code is proven correct, so there cannot be bug in the code. Like there cannot be bug in the proven part. Especially if we have proven the right property, we can rule out many of the hypotheses of why exactly a crash is happening. So it can help a lot in debugging. Like when something is wrong, if we have a lot of proven parts, you can focus on the rest things, the unproven parts.
So the general workflow for like just like writing a proof is like you're just defining these pre and post conditions, and like if the proof doesn't compile, then you just have to go into like what you're missing, and just like kind of like update your pre and post conditions.
Yeah, we can see an example if you have time. I'm all day here today, so anybody has questions. So we can go, and we'll also go if people have to go. We'll also repeat that in the next lecture. Yeah, but that's roughly like you by looking at the mismatch, you can guess often like what is wrong, and you go back and fix the specifications, or sometimes the loop invariants we have to write by hand. In this case, like when we are splitting, do concurrency reasoning, we're creating a new thread, we often have to sometimes by hand. So it's not completely automatic to like to decide what resources the new thread is getting. So like in execute block function, we are like creating a thread in a loop. So here like we are starting a thread in a loop. Like every thread is creating a new, every loop iteration is creating a new thread. So it becomes a slightly bit, it's hard to completely automate that. So those things, we make some choices in the proof, and we often have to go back and refine those proofs until all the pieces put together. Like it's like an addictive game, until all the pieces of the puzzle put together in the new QED, and then okay.
I just saw that you had the same question written down, but I was thinking, so how would this look like in Rust? Because in Rust we have ownership, and so all the memory, like would our proofs get simpler because we can leverage the ownership to reason about the permissions of the memory? Or yeah, I mean, would the verification become simpler in Rust?
Yeah, I think like the specs would look almost, maybe even the spec can be inferred by the ownership discipline, like by the ownership annotations that you have in the code, that can be used to infer specs more easily. And it also some steps in the proof where we have to decide whether the caller is borrowing the ownership or not, when to do the split. All those things can be automated more by using the type checkers, how the type checker had decided the ownership flows. Those can be hints in the proof. So yeah, definitely that can help. Any other questions from the Zoom folks? Right. What should we do? So you wanted to look at the proof, we can do that, or should we leave and come back, or should we just look at a few proofs? Whatever.
I mean, I kind of want to look at proofs, but
Okay. Yeah, any other suggestions? Do people want to take a break before? Yeah, anything I cover in this session, I will repeat it in the next session because it was overtime.
I guess like tangentially like related, but what parts of execution are you like kind of is like on the list to formally verify?
So I typically like to start at the top. So oftentimes what happens is like you start at the bottom, like, and then you prove some functions down the call chain. And then you go and prove the callee. You figure out that things don't fit together. So I like to start at the top, and then decompose that like for this top level function, like for execute block to have the spec, these callees must have these specs. So I refine and refine and refine. So what I've done so far is I started with execute block, finished with proof, but that proof assumes the spec of execute transaction. So that was the first proof I did. Next, I looked into execute transaction. I did that proof, but that proof assumes the spec of this function execute impl to there's some function. So that spec is still assumed. Then the next I will look into, so I'll slowly going down the call chain. So at every step I prove a function, then I look at which of the callees of this function is the most tricky and most likely to find bugs. Then I go in and verify that function one level, and I keep going down.
But what do you do when the code changes? Like presumably you have to update your proofs, and the proofs did seem like they were referring to specific parts of the code, and like
Yeah.
they to me they look a bit brittle, right? I mean, if the code changes, it could very easily be that the proof breaks.
Yeah. So I was doing things very manually today just to show how things work, but we don't like the splitting that I showed. You don't really have to do manually. Like you can figure out that you need half and you have one, you can automatically take split and half, take half, automatically join. There is a lot of things that can be done automatically. I just showed.
And so when code changes, do you update your proofs or?
Yeah, it's a like there's no like in my previous company we maintained many proofs for 5 years, and sometimes it can be a chore. Like things change. So there are some best practices to how to write more maintainable proof, but there's no like good science of that. Like people are still, and yeah, especially when we involve LLMs. What exactly we cannot like when we replay the proofs, we don't want to do the LLM search again. So we want to remember something and put it in the proof script, and how do we update? So there are these questions that there are no like great answers right now.
Are the proofs on GitHub? All right.
Yeah, the proofs are on GitHub. I posted a link in the formal methods channel, so that has a link to the both of the files, the C++ file and the V file I showed.
All right. So the proofs for execution, those are
Those are in the same branch. If you in the same branch, if you look at execute block proof, I can tell you like I mean if you look at all the V files, there'll be just a few. Okay, should we look at more proofs, some proofs? Okay.
yeah. That's the one.
So we meet now, or do you want to stay? We can do whatever. Okay, sure. So
Okay, so I guess like GCD would be the simplest proof. And this is a proof that like the tool I built in my previous company just last at the end, just leaving, we do completely automatically. So in these proofs, like with loops, the only tricky thing is this loop invariant. That's the only thing that we don't have algorithmic ways to solve in a nice way. Everything else can be solved algorithmically. So I have like an algorithm with LLM in a loop to do these proofs. So before LLMs came along, we were struggling with like loop invariants. Like there was no good way. But now we can just ask LLM for the loop invariant. And if it guesses wrong, we show why it's wrong. And we ask it like, do you think you made a mistake in the loop invariant? Is that why you're stuck? And then it often tells you to go back and I want to update the loop invariant and so on. So
loop invariants are the undecidable part of formal verification.
Yeah,
so
yeah.
it's the LLM only gets to that far.
Yeah. But the thing is like for GCD and these the other things that where it worked nicely was the linked list proofs, like linked list, merge sort, and all that. You have a linked list and you merge sort a linked list, and so they're even there. Like the exact algorithmic why it's correct is there in textbooks, which LLMs have read, and they're good at translating it to this kind of formalism. So once I've explained to it like what is the syntax, it can convert that knowledge to this particular syntax and do the proof. So this is the function. This is the proof of GCD. Let me actually open the code as well. So this is the GCD function. Okay. So we start the proof, and it's now it's stuck at while. So this is the problem. So one thing that the automation doesn't do is like for while loops, it just doesn't do anything. It just waits for the loop invariant. It asks me to write the loop invariant. So can somebody tell me without looking at this, what like even in terms of English, what is the loop invariant of this loop? So just to remind, what is a loop invariant? So the loop invariant is some property that is true at the start of every iteration of the loop. So it's some property that is true at the start of every iteration of the loop. So obviously that's like under constraint. Like you can just pick true, and true is always true. But it should be strong enough such that when the loop exits, something important must be true. In this case, when the loop exits, the post condition of this function must be true. So it must also be simultaneously strong enough such that if the loop invariant is true and the loop condition is false, that implies the post condition of the function. So let me write it down. So loop in is something that if you start from the loop invariant and run the loop body, then you get back loop invariant. So it's something that is preserved by the loop body. That's how it's always true, because when you run the loop reestablishes the loop invariant. So that's one property the loop invariant must have. The other property it should have is loop invariant in conjunction with the negation of loop condition must imply, in this case, like the post condition of GCD. Which is like, in this case, it should say that A equals GCD. A at that time is GCD.
And the precondition should imply the loop invariant as well, I guess, in our case.
And the precondition should remain, yes. So there are three constraints in choosing a loop invariant. And why am I using Coq syntax in C++? Okay, so what is a loop invariant? Why? Yeah, what is a loop invariant here?
I mean, this loop invariant, right, it's just like, it remains true while A is not a multiple of B, right?
Yeah. So yes, that's a good point. Loop invariant and loop condition. Under that condition, only under that condition, you have to reestablish the loop invariant. That's a good point. Sorry. And this is separation logic, so these are like embeddeds.
But the loop invariant itself does not have any.
Yeah, in general, like in this case, loop invariants are embeddeds. And this is also important. Like for example, if we see this, the execute block function, like it is in a loop. It's calling threads. Where is
Wait,
it?
so did you say it does or it does not have
Ownership? Yeah, the loop invariant is an embed. The loop invariant in this setup, the loop invariant must be an embed. In separation logic proofs, loop invariants are embeds.
in print?
Embeddeds.
Yeah. So they have ownership.
So like if you like this happens at execute block, if you fork threads in the loop body,
Right.
then you have to keep track of how much ownership you have left.
Yeah. So is that already the solution up there? Is that the loop invariant?
Yeah, that is the loop invariant. Where is it? Where is the file? Okay, so intuitively the loop invariant is that even though A and B are changing in the loop, the GCD of A and B must always be the GCD of the initial argument, the initial values. So that's how we write it in the formalism. So this is saying that, so at this point, we know that the initial values are BV and AV. So that's fixed. Like these are Coq numbers. So they don't change. Like so we are given these initial values. Let me rename them so that it's more understandable. Rename AV into AV init. Okay, so and then it's saying that when the loop progresses, the values of A and B, so what is stored at the locations A address and B address will change. They will have some other AV prime and BV prime. But what is true is that their GCD is the same as the GCD of the initial values.
So initially it's trivial to prove because the left-hand side is equivalent to the right-hand side.
Yeah. So
A and B are equivalent to A in it and B in it.
exactly. So
in each iteration, we just perform one step and it's still the
one
same.
body, we do one iteration. We will see all those steps. Once we give the loop in, then Cork will ask me to prove all those things, to do all those things. Yeah, so Cork will ask me to prove all these
And
things.
in the end, we know that the B is 0 and the GCD of A and 0 is A.
Yeah.
Right. That makes sense.
And these two things we also have to do. This is the C++ issues. We have to remember, if we forget this, so even though the values change, sorry, should you ask? Yeah. Okay, so at this point we tell Cork that that's the loop invariant I want to use, and then Cork tells me, okay, then prove this part that the precondition enters the loop invariant. So it's telling me already prove now that you have the loop invariant, which is fine, which is we execute essentially, as you said, AV prime by AV init, BV prime by BV init. We don't have to really have to do it by hand, Cork does all of that.
So does it automatically instantiates the existentials or?
Yeah, so this is safe, right? So this is in this case. So in general, in any Cork proof, instantiating an existential is a dangerous step.
Yes.
If you choose the wrong value, you are screwed forever. So, but in this case, the automation sees that we know that A address is AV init. So, and then AV prime is the value of A address. So it knows that the A address can only have one value, right? The A address, whatever is at A, there's only one choice. We know the A address cannot have two values. So it is sound. We cannot go. This is a safe proof step. That is, you cannot go wrong by choosing AV prime with AV.
So it instantiates the existential if only if it knows that it can't go wrong.
Yeah, only if it's a safe choice. Only if it is guaranteed to not make the proof unprovable. Right. Only then it instantiates the existential. Like for example, it did not instantiate the loop invariant. The loop invariant is also an existential if we unfold these notations, but it did not because there is no you cannot completely automatically figure out what it is without understanding. So, but in this case, there is a completely automatic way to do a safe choice, and SL Auto does all that. So this completely discharged the first this part. So now okay. So now we are at the first thing that the while loop does is checks the loop condition. So this is like we are doing a branch on BV whether BV is not equal to 0. That's exactly what's happening here. So we have to make cases. We've said that make two cases. So we are running now. This is the loop condition true case. So and notice our context is generalized. We do not have AV at A. We do not have AV in it. We have AV prime. We have some arbitrary AV prime. So now we're not starting from the initial state. We are starting from the loop invariant. So it has changed our context. But our wallet is now, it corresponds to the loop invariant. Okay, so now we run through the loop body, which is, and we're quickly done. So it's not like these simple things. I think this is unsigned, so there is probably no precondition from that. So there is no precondition for any of these. So it just runs through the code. And at the end, we are saying, just want to highlight this, that we are destroying, the next step is to destroy this temporary called temp. We created a temp in this body, and at the end of the loop body, we have to give up the full ownership of that temporary. So which is fine. We have the full ownership of the temp body. So this just prevents you from giving it out to some other thread. Like you cannot like here take the address of temp and give it to some other thread to write to it. You don't. It prevents those kind of UBs. So you have to, at the end of the body, you have to completely give up all the ownership. So now, and then you have to reestablish the loop invariant. This is saying that give up the ownership of temporary fully and then reestablish the loop invariant, prove the loop invariant. Again, because Coq knows these things, like this also automation knows this, it knows that B has that value, and then it has to choose a value for this. There is only one possible way to make this work. There is a sound choice here, so it will completely automatically make these choices. It will instantiate BB prime with this value. And a V prime with this value to match this. We will do it completely automatically. So what we are left with is just this, that we need to show that that the new values of A and B are the GCD of them is the same as the old values.
And do we have the and we have the corresponding precondition we have from the previous
loop
variant,
yes.
we know that the GCD of exactly that.
Yeah, before the loop this was true.
Yeah.
So we started from the loop invariant, so we knew this from the loop invariant before the code started running. So now we have to reestablish this.
So we probably have to unfold the GCD definition once, right?
Yeah, you can just look at the standard library. It already has something. So I mean, I think this is great. Not many languages have this. You can just say search, give me all the lemmas about GCD and mod. And then you will find it quite quickly. So you can constrain the search. You give me the lemmas of this shape, that shape, and then you quickly find what you're looking at. So this is exactly a lemma. Already in the standard library, we don't have to do anything. Like it just says that GCD of A mod B, B is the same as BA. And what is that? This is rewriting on the right argument of GCD, and here this lemma says something about the left argument. So we have this tactic in the standard library to rewrite modulo associativity and commutativity. So GCD is both associativity and commutative. And so this tactic is smarter. So when I started doing this proofs with LLM, this was the problem. Like LLMs would not, it does proofs like the regular mathematicians do, and they don't care about these things like we have to first reassociate and recommute and then rewrite. It would already mess this up. So with the help of Coq folks, they had something, I improved it, and then so whenever the LLM says that rewrite with that lemma, I actually rewrite modulo associativity and commutativity, and then that's done. This part is done. And quickly, the last part is when the loop condition was true. So sorry, the loop condition was false. So in this case, we know that BV is true, B is 0. So in this case, we would not run the loop. We will just return A. So again, that game, like the C++ semantics computed this, but our spec requires this. That we need to return that at the return value. At the return location, we should have GCD of AV in it and BV in it. But this is what the code does. So we need to prove that they're equivalent.
And what is CQP?
Yeah, this is some syntax thing I wanted to hide.
This is the same thing I asked about already.
Yeah, we can ignore that for now. It's just a fraction. The fractions are 1. That's not a problem. The problem is the values don't match. Which is fine.
We only need to simplify.
Yeah, so
0.
So we look at this. So we can look at this. So in this lemma, the left hand side. So we can rewrite this. So there is this lemma in the standard library, which says that GCD of n0 is n. So we rewrite that with that in this hypothesis. Not sorry. In this hypothesis, and then okay. So now we have AV is GCD of AV in it and BV in it, and then when we substitute, we are done. Then they match up. And this, when we rewrote this lemma, there was this side condition that the thing was greater than or equal 0, which we already have in the context. Okay. So that's the proof.
I have a conceptual question, which is in the proof state, it looked like you had the WP, which is weakest precondition, right? And I always thought that the weakest precondition is that you started from the post condition and you work backwards to the code.
Exactly. So that's.
But we always went to the code like from top to bottom. Like maybe this is a bad example because we have a loop, but initially, like in the first example you gave, we had this like y equals 0 and then y equals x plus 1. And we started first with y equals 0 and then we did y equals x plus 1. But if you compute the weakest precondition, you should start with the last instruction, right? And then move up. So I didn't understand how that works.
I think we can go both ways. Like weakest precondition, there is a rule to like simplify it for sequence. So like WP of C1 command and then command Q, that is equivalent to we first do the WP, the weakest precondition. So for anyone else who may not know VP, so weakest precondition, this notation, weakest condition of the command C, this means this says like what is the weakest embed such that when embed like say P such that when we run C from P, Q holds at the end. That's what WP, and that's what the logic defines. And so there is this rule that weakest precondition of C2 Q that has a nice like algebraic equation saying that WP of that of C1 starting from that post condition. So this is the rule that we have been using. Like if we have a semicolon, then we can first prove we can start proving this one. And then we keep peeling off the commands one by one and until nothing else is left. In that point we do Q. But I think you're right. We can do it from the backwards also. Like both choice. Sometimes actually I do have to do it in backwards cases, especially when I do like infer the spec of some lambda. If I want to infer the spec of some lambda, sometimes it's useful to do it backwards. But I haven't done it much, so I can't tell you. We have been doing like forward.
Can you actually write them? So the proofs that you've shown us so far are kind of, I mean, in Isabel, we call it apply style. So you have a proof goal. You start with the goal and then you massage your goal by like applying lemmas and things like that.
Yeah.
So you kind of start with what you want to end up with, and then you try to go back to like removing the goals essentially. Is there also a way of proving like forward start proofs? So you start with what you know, and then you state like, okay, now from this I can infer this, and from this follows, and at the end I have the proof goal. You know what I mean? Like instead of starting with the goal, you start with your assumptions, and you prove your steps in a forward direction as opposed to in a backward direction.
But this was very much a forward proof, right?
No, because you start out with the goal, as I see it, right? And then you apply like you apply a lemma, let's say, for the GCD, and it always tries to solve the goal. So it always you start out with the goal. Whereas what I'm talking about is like if you were to write down a mathematical proof on a piece of paper, typically you would start with your assumptions, and then maybe you have like a helping lemma that you can prove, and you start from the assumptions, and at the very end comes your goal.
Yeah, so they're both good. So there are places where that style is good. There are places where that. So the main thing is we want to minimize how much we have to do by hand.
Yeah, so it's more by hand proof.
So yeah, so that would require more proof. We have to guess what the WP would require next. But this computation already tells me what is needed next, so we don't have to guess. So that's why this.
But so I'm asking because in Isabel there are these two styles, and this just so there's the apply style, which is where you take the goal and you massage the goal, and there's the ISAR style, which is like writing down the proof from top to bottom. Do the same things exist in?
Yeah, it's the exact same thing. Like you can keep asserting new things, and you can do that in Coq, but many times that's requires more writing things by hand, and it's not ideal.
That's true. It's more explicit, I guess.
Yeah. So our goal is like to make it completely automatic. And so as I said, this proof was completely automatic. Like you see, I have this tool which run in Emacs, and it will print out the proof by talking to LLM. And for GCD, like 9 out of 10 times it will do it correctly.
Wait, so this is completely automatic? What do you mean?
Not here, but I have a tool that I built in my last company, and they haven't yet given me access. Waiting once I get that, like that tool for these kind of proofs, it would completely, you just at this point press a key binding and it will one by one fill exactly this out. I just copied here what my tool had actually.
And it uses an LLM or it uses?
It uses an LLM just for the looping variant. Also sometimes for like searching the library for element. But mainly for the looping variant. In this,
Yeah, okay.
And it will emit this proof because we don't want to, like, once we have LLM has discovered a proof, we don't want to run LLM every time we compile this file.
But is there also, I mean, like besides LLMs, are there automations in Coq that? So I know for Isabel you can try the sledgehammer and like it tries to find like a proof automatically.
Yeah, we have
to
this
use an SMT solver to try to find a proof, things like that. Does that exist in Coq?
Yeah, there are some tools. We haven't used SMT, but this SL Auto is pretty good automation. I didn't work on it too much, but it's very extensible. You can add one symbol, and you see that you can cancel, or especially for existentials, you can say that if you see this in the context, you can like soundly infer the existential quantifier. You can give those hints, and then it will pick it up and automatically do this.
This is actually done different in Isabel. In Isabel, if you have an existential, like if you apply the auto tool, it will try to instantiate it, and if it can solve the goal, then everything is great. But if it can't solve the goal, it will not instantiate it. So you always have to instantiate it manually. But in that case,
so this is something we wrote to a custom, like at a previous company. So where this is not SL Auto is not by Coq. It's a very sophisticated algorithm. It uses Prolog, all those things. And I don't know the details of this, but yeah, it's extensible, and we can write this. For example, I had to like disable this hint here to automatically split, so that I could show you how the automatically split. But if I add it back, it will just automatically do the splits. And even like as GCD, like it automatically figured the existential quantifier. So I have to manually remove those hints, otherwise it automatically